For robots with links and joints forming closed loops, it is often easier to find an implicit representation of the C-space rather than an explicit parameterization. Consider the 4-bar closed chain shown here. Grubler's formula tells us the 4-bar has 1 degree of freedom, so it should be possible to parameterize the C-space by a single variable. This representation may be hard to derive and may have subtle singularities, so instead we could view the C-space as a one-dimensional space embedded in the 4-dimensional space of joint angles, defined by the 3 loop closure equations that say the final position and orientation after going around the loop must be equal to the initial position and orientation. If we define the vector of joint angles theta, we can rewrite the loop closure equations in this vector form. These constraints are called holonomic constraints, constraints that reduce the dimension of the C-space. If the robot's configuration is defined by n variables subject to k independent holonomic constraints, then the dimension of the C-space and the number of degrees of freedom is n minus k. If the robot is moving, we could ask how these holonomic constraints restrict the velocity of the robot. Since g of theta has to be 0 at all times, the time rate of change of g must also be 0 at all times. We can write these constraints as a matrix dependent on the configuration theta times the joint velocities theta dot equal to 0. If we call this matrix A of theta, we can write the velocity constraints as A of theta times theta dot equals 0, where the A matrix has k rows and n columns. Velocity constraints like this are called Pfaffian constraints. Sometimes we call holonomic constraints integrable constraints, since they are essentially the integral of these velocity constraints. In some cases, though, a set of velocity constraints cannot be integrated to equivalent configuration constraints. Consider the chassis of a car driving on a plane. If we define an xy reference frame, we can represent the configuration of the chassis as q equal to phi xy, where phi is the chassis angle and xy refers to the location of a point halfway between the rear wheels. If the forward velocity of the car is v, the xy velocity is x dot equals v cosine phi and y dot equals v sine phi. We can express v as y dot divided by sine phi and substitute this into our equation for x dot to get the velocity constraint x dot times sine phi minus y dot times cosine phi equals 0. We can write this as a Pfaffian constraint a of q times q dot equals 0, where the single row of the 1 by 3 A matrix is 0, sine of phi, and minus cosine of phi. Unlike a holonomic constraint, this velocity constraint cannot be integrated to give an equivalent configuration constraint. Therefore, we call this a non-holonomic constraint. A non-holonomic constraint reduces the space of possible velocities of the car. The car cannot slide directly to the side, but it does not reduce the space of configurations. Sideways motions can be achieved by parallel parking, and the car can reach any configuration in its 3-dimensional C-space. A robot can be subject to both holonomic and non-holonomic constraints. Again, using the car as an example, if we consider the chassis to be a rigid body in space, then 3 holonomic constraints keep the chassis confined to the plane, while 1 non-holonomic constraint prevents sideways sliding. To summarize, holonomic constraints are constraints on configuration, non-holonomic constraints are constraints on velocity, and Pfaffian constraints take the form A of theta times theta dot equals 0. Determining whether Pfaffian constraints are actually holonomic configuration constraints or only non-holonomic velocity constraints is left to Chapter 13. In the next video, we wrap up Chapter 2 by introducing the task space and the workspace.